try one of the my transparencies in case. Thank you.
Oh, that's all right. Our next presentation comes from joint work at Notre Dame, BP Research Center, and Argonne National Lab. The title is In situ XF's Activity and Characterization Studies of the Effect of Chlorine Poisoning on Platinum Alumina Catalyst during Methane and CO Oxidation. And the authors are F.G. Garcia, W. Lee, E.E. Wolf, J.T. Miller, A.J. Kropp, and the talk will be given by Dr. Wolf.
I'm a loud guy, I assure you. Okay. Well, this collaboration with our department, Francisco Gracia actually, Jeff Miller at BP, I understand this is no longer valid at this moment. So he gave half of the talk in the morning on my behalf, and Jeremy Croft, who is at Argonne National Lab, and who did actually help in getting the XF data. But this is really a combination of the two things. The XF alone won't give you the whole story. Activity is as much part of the story as the other data. For many years, we've been trying to establish that the state of the metal surface is related to how you prepare your catalyst, the support that you use, and the reaction conditions that you use. The problem is, most of the time, we cannot do all these things because the techniques that we use for characterizations are ex situ. And we know that from the literature data, there are significant differences in activity depending what is the state of the surface and if we have absorbed species. And we just heard of an example where carbon was one of those strongly absorbed species. Now, in many cases, we use chloroplatinic acid for catalyst preparation, and it turns out that chlorine is a significant poison for oxidation reactions. So it is possible to eliminate chlorine, and if you know how to do this, then the effect doesn't show up. This is the reason why it's such a discrepancy in the literature, because people use different methods of preparation and pretreatment. So we're going to use two catalysts, one that have no chlorine and standard impregnation, wet impregnation with a platinum ammonium nitrate on alumina, and we're going to call this a platinum with no chlorine. We calcine this at 250 and then reduce in order to do chemisorption. And if you do this with this particular precursor, you get pretty high dispersion. And this is one of the requirements if you're going to do XF and relate the results to surface concentration. This was then oxidized in air before reaction, so the conditions are similar to those that we use in reaction, and as we'll show, this is very significant. And when we do this after oxidation, we can see CO chemisorption as well. The other catalyst was you prepare with the chloroplatinic acid on gamma alumina, and we're going to call this chlorine-containing and chloroplatinic acid because to demonstrate some of these effects, we have also prepared catalysts in which we added HCl in order to introduce chlorine. Now, this catalyst, it turns out that chlorine had a good effect on preventing sintering. We want to maintain very high dispersion. You can do that with the chloroplatinic acid, but not with the other catalysts. You sinter it, and we reduce it, and we are able to get pretty high dispersion with this catalyst. This is not the case, for example, if you're working with silica. So all these things have to be accounted for when you're doing these reactions. Elemental analysis indicates that we do have chlorine, and again we do the oxidation in there, and we see no CO chemisorption at room temperature. That doesn't mean that there's no CO chemisorption at reaction temperature. Okay, so how do we obtain the data? This we do in a recycled reactor. Recycled reactors are very useful when you have high rate, because you can calculate your rates at any conversion level, okay? And also it's useful when you have exothermic reactions, because the high flow rate that you circulate on the reactor system allows you to maintain pretty isothermal conditions, which otherwise will be difficult to obtain. Normally, so this is a typical profile of conversion versus temperature. And if you don't do this in a recycled reactor, what normally happens is the conversions jump to the high steady state at one point all by itself. Here you can really measure up to 50 or higher conversions if you want. We try to stay below 450 to prevent any sintering complicating the results. Now here there is a significant temperature difference between the two catalysts. I should also mention that we use a very dilute feed so that we don't introduce the effect of carbon, but if you use higher carbon concentration, the results also change. It's an oxidizing environment. This is the standard flow rate on the reactor, but there's a recycle ratio of 20 so that we can calculate rates as in a CSTR, and we normalize those with the initial area that we measure at room temperature, and we have activation energies here that change a bit, but not too much. And but the important thing is that here we have these activation energies, and the fact that here we have very little reaction at 350. There is a very significant difference in rate, about 20-fold difference between the rate with chlorine, without chlorine, and no chlorine. If we do a calculation under this condition, of course here the sites are being opened up, but under those conditions where we do this comparison, 95% or so of the sites are blocked by chlorine, so that you get that low rate. If you have a one-site model, about 75 or 70% if you have a two-site model. Well, we started with methane, and we thought, well, CO oxidation had to be somewhere there, and so we repeated the results with CO oxidation pretty much under similar reactant concentrations and flow rates. And again, we observed that the chlorine and chlorine-containing catalysts have significant differences. The temperature change here is about 50-degree difference. Have in mind that the rates double every 10 degrees at temperatures around 150. So this is about not as large as in the case of the methane reaction, but still it's an order of magnitude difference in the rate at 100 degrees centigrade. So very little reaction there compared to this. We can do these calculations at high temperature. The indication by simply looking at the change in rates is about 90% of the sites will be blocked by chlorine for a one-site model and 70% for a two-site model. So again, for CO oxidation, we see sort of the same kind of behavior, except that here there's some variation in the activation energy. Not so sure about that, but then we thought, well, it's valid for CO and C1. Let's see what happened with C2. And sure enough, it's the same effect. Chlorine-containing catalyst, a lot less active than the one without chlorine. Activation energies here are pretty much the same. And let me see. There you go. And the rates difference again is about 10 Now the temperature now is different here. It's a little higher than in the C oxidation case. It's less than in the methane oxidation case. So again, we have, and again, if we do these calculations at this particular temperature, we get about 90–70% size blocked by chlorine. So chlorine is a poison for oxidation reactions under these conditions. These effects vary also with the feed concentration. So the state of the surface is defined by the precursor you use, by the reaction conditions that you're using, and how you pretreat the catalyst. So you can get results all over the place depending on how you do this. Okay, now what we wanted to prove was to say, oh well, let's start with this catalyst and let's add chlorine to it. And so the catalyst without chlorine is pictured there with the cartoon. And the first results that we obtained was sort of disappointed because it didn't show the effect as much. Here we added about 2% chlorine, and when my student didn't calcine the catalyst, and it shows about the same activity as the no-chlorine catalyst. I said, well, something is wrong here, so why don't we calcine the catalyst? So this very same catalyst was calcined now at 250, and the chlorine that was hidden on the support. And this is very interesting because it's a very dynamic behavior of what's going on the support and on the surface of the catalyst. Sure enough, it went back to the surface, and there you have a decrease in activity. And if you keep playing with this, now we did it at 300, more of the chlorine went onto the surface and sort of had the same effect as when you started with the chloroplatinic acid catalyst. So it turns out that the calcination now drives the chlorine from the support onto the metal. And you can ask yourself the question, can we do the reverse? And the answer is yes. So you can drive the chlorine off the metal and in fact into the support again and back and forth. So it's pretty tricky to get rid of all of it. Now, if in fact we do the same thing with an excess chlorine now with 5%, the other one sort of was stoichiometric with the amount that we used in the preparation, and calcine at 250, then we have a very, very significant difference in these rates. I mean, these are, I didn't even calculate that. But if you go back, then it starts getting better. If you go back on your calcination treatment, a little higher temperature, start getting better, and eventually you end up with this same line because the chlorine is coming back and forth and eventually out of the reactor. So you can clean the surface eventually by subsequent pretreatment. So, well, we thought, that's very interesting, let's try methane oxidation. We see if the pretreatment makes an effect. So here we have our two base catalysts, no chlorine and chlorine-containing catalyst. And these are the other catalysts in which we added the chlorine and no effect of the pretreatment. So here again, what's going on? No pretreat, the same as when we calcine. And well, what happened here is this reaction, temperatures are very high. So what you're doing as you're moving towards reaction, you are calcining the catalyst. So the pretreatment really doesn't matter. It's your reaction that is doing the pretreatment. Okay? So again, you have to have all these factors into account. It's not that chlorine doesn't have any effect. It's just, it depends where it is. Okay, so this is a repeat of what I said. And the other thing is that at this higher temperature, apparently there is some sort of an equilibrium coverage of the chlorine that you reach at the higher temperature. Now, we took a catalyst just out of the, just after preparation, no calcination or anything. So for C oxidation again, this is a chlorine-free catalyst. This is calcine, and with no pretreatment. In both cases, we got an oxidized surface. Okay, obviously we're calcining the catalyst. We are reacting the reaction itself. Now, can we reduce the catalyst? Yes, we can, and then it's a lot more active. Okay? So again, here, depending on how you started in your pre-treatment, you end up with significant differences in activity. And so this is the reduced catalyst, and we can sort of go back and forth on this. We calcine and reduce again, but there is some resistance to the reduction after you calcine, and you need more time. In fact, I just told my student yesterday, you need 40 hours to get rid of the chlorine at 450. If you do it for 3 hours or 4 hours, your chlorine is waiting right there and your support ready to jump onto the metal. Okay? What is there? Okay, this is the chloroplatinic acid, again calcine. It's less active than the one without the chlorine. So everything is consistent, providing that you have into account that now this is what we normally do in our lab, the reaction part. This is where the collaboration with Jeff Miller and Jeremy Croft came out. Argonne National Lab put this fantastic facility with very high intensive X-ray synchrotron radiation. The main advantage of this is that we can do this at room temperature. Okay? And the main thing about this is that these are conditions that we use. And this is the important part. We do this, and I would say quasi in situ. All right? An important thing is that this is, the catalyst is there in a little holder, very thin, and we take it, you see two valves here, we take it to, there are very strict regulation in this national lab, so we have to take it to a hood, connect it to the system, and we pre-treat it under the same conditions that we have used in our reaction studies. And then we cool it down. So it's not at the same reaction temperature, but the reaction environment, which is what defined the surface with the reaction temperature, was similar, and it was sort of frozen in this system. And then we take this into the facility there. We do all this at the Argonne National Lab, and we put it in the beam. These are the two detectors. And we do this in a continuous flow. This is where the furnace is. And we obtain the data at conditions after pre-treating under various conditions. And the key about XF is that you have to have very good standards. Otherwise, you can do a lot with your fits, because there are lots of parameters there. And I don't know much about it, but Jeff is very much an expert, and he's done a lot of samples. These are the standards that he uses for assigning all these distances and coordination numbers. And so he can look at the spectra and pretty much decide what's important, what's not important, and that's why it's important to know what's happening with the activity. Because if you don't have the activity data, it's not that simple. Because you have to fit this in order to interpret the data. Okay? So here we have both the magnitude of the raw data for the no chlorine and the chlorine catalyst, and just by inspection you can see that these are indeed different. And then we have the model fit in the blue line. We're fitting basically mostly this part with discarding that part. The imaginary part of the raw data is the dotted line, and the imaginary part of the model fit is the dotted black line. And the model fit will tell you what are the distances between the scattering distances as well as the number of nearest neighbors. Okay, we keep served with the activity data. So now we have a very nice fit. Well, when we start with the chlorine, these correspond to the the coordination number of 6, octahedral coordination, and that is proper distance for platinum oxide. Calcine at 250. Very similar to what we use at the reaction. Then we reduce the catalyst, and when we reduce the catalyst, of course, we see the appearance of platinum distance as one would expect. You have platinum, and we also, these are so thin and small particles that you can also observe the platinum oxide distances platinum coordinated with one oxygen, and this is a little different because we think that this is the coordination with the alumina support. So you can gain quite a bit of information by looking at the spectra. And when we take the reduced catalyst and we oxidize, we recover some of the oxides. So and this is a function of time. Naturally, if you do it at a longer time, then you're going to see different coverage of the various species here. We see that these small particles are rather resistant to oxidation. So we see the platinum oxide as well as the platinum as well, 2.7 to about 210, I believe it is, the distance for the oxide. Now this is the interesting part here, which we did not expect and really confirm it, our results with the activity. Now there's no surprise here. Calcine, we see the platinum oxide as well as the platinum chloride and the corresponding coordination. We're not sure whether these are independent species or there is an oxychloride complex on the surface. We just put it that way so that we don't have controversy which one it is. We can say, well, it is one or the other, right? So anyway, so calcine, no problem. The right distances for the platinum chloride and the platinum oxygen as well. And again, when we reduce similar results, the right coordination numbers and distances, some of the platinum oxygen due to the support here. And now you see that we put the chlorine out of there because of the reduction send the chlorine out. And the interesting thing was that when we oxidize this, which is really what confirmed everything we've done with the activity, we see again the appearance of platinum chloride. So what happened, that the chlorine that was here went back to the surface. Okay? And again, I insist it is possible to get rid of this if you do it for a long time and higher temperature. We use this milder treatment so that we don't have sintering. But if you do it for, as I say, 40 hours was the last result that we came out. It's pretty difficult to get it rid of, out of the alumina, not so out of silica. Okay? So if you've done the preparation on silica, which I don't have, you will tell me, oh, it doesn't matter. No, it does matter. On silica, the difference, the temperature shift is about 50 centigrade. All right? But when you reduce it, it's fairly easy to get rid of the chlorine on silica because it doesn't stick to the support, the silica support, as much as the alumina support. Okay? So when you oxidize again, then it looks like you have your chlorine-free catalyst again. So this is sort of the gist of the story here. The exciting part is that now we can extend this to a number of other source species. We're looking at sulfur, and so I insist again, low reactant concentration, because we have data that shows that if you increase the concentration, the results are different. The presence of chlorine affects the activity of these catalysts for CO, methane, ethane oxidation. Of course, this depends on the pretreatment, reaction conditions, and support use. If you use zirconia, you're going to get different results. If we add intentionally this, you end up with the same results as when you start with your chloroplatinic acid. So you can be intentionally doing, and I'm sure, and this is done in industry actually, for certain reactions where you need to have the chlorine there, and part of the chlorine will end up in your metal and improve your selectivity most likely, or in your support and improve your acidity of the support. And there is a migration of chlorine from the support to the metal surface. I don't know how fast this occurred. Reduction, of course, gives you the metallic surface, which is the most active for oxidation reaction. But if you do these things for a long time, you're able to eliminate the chlorine from the surface. And what we concluded from the combined kinetic and EXAF is that chlorine is blocking the metal surface decreasing the number of active sites. And we have done the calculation also with a fairly sophisticated Monte Carlo simulation program, and we end up with a 67% blockage of the surface compared to these very simple calculations that we did here. So that's what I meant to say, and I already said it. So finally, show me the money. The money is here, and thank you. This is a very successful collaboration between industry and academia, which is whatever the name of that program, but it works. Thank you for your attention.
Questions? Yes.
Have you done the chemisorption experiments when you put your chlorine back by this porthole effect that you have? Does the chemisorption of hydrogen decrease when you get the chlorine in the metal?
It should. It should.
Or would you react that off with hydrogen if you want hydrogen over the gas?
It depends on the temperature you do it. If you do it at high temperature enough, yes, you will. Right. At room temperature, we don't even chemisource CO. But CO has to be chemisourced as we increase the temperature, and there is some sort of an equilibrium. You start opening the sides, as a matter of fact.
I suppose one could get sophisticated and vary the concentration of the noble metal per unit surface area and then investigate the HCl addition stoichiometry to see the migration path that it takes to give that coverage. I'm just curious if that number that you get from XFs is really real. In other words, could it be possible that really a small amount of chlorine is causing the deactivation that you're saying, and that somehow or another that coverage of 70% is for some reason not the real causative agent in the deactivation?
It's very real. Now the reason, but it's a function of the temperature, and we haven't done the calculation at different temperatures. Okay, so when you see the two curves, one, the chlorine-containing catalyst, is a low temperature curve, and the one with chlorine, the no chlorine is a low temperature. The one with chlorine has no activity at those temperatures. But as you move up in temperature, obviously some of the chlorines will start moving up, and so I said this is 60-something% at this temperature. We sort of standardize at 20% conversion, blah, blah, blah. But yeah, it changes with temperature. Obviously, you're gonna. But at that temperature, it's very, very real.
Question. First, did you detect any chlorine-containing compound for methane oxidation at high temperature?
Do I detect a reaction between the methane and the chlorine on the surface? That's your question.
Yeah.
I didn't measure it, so I didn't detect it. But at these temperatures, we can go back and forth in these results, okay? So at these temperatures, we don't have a lot of leakage out of the system, okay, during these reactions. It takes about, I say, 4 hours to run the whole temperature spectrum. Eventually, yes. Eventually, yes.
Okay. Second question. What's happening if you use low chlorine concentration, like 10 ppm, 100 ppm, instead of like 2%? What's happened to activity of gas?
Guess what?
Huh?
It won't be that much, right? If you put less chlorine, you got activity that looks like the one that have no chlorine. So the answer is yes, it's a function of the chlorine concentration too. But the question is that we started with the chloroplatinic acid that had about 2% chlorine, and that's why we did it with 2%. But you're right, if you use less, you got less deactivation. You're very welcome. Yeah. I don't know, Al.
Eduardo, you can distinguish the chlorine species by GPR. We have done that.
Yeah.
And what we have found is finally, when you increase your temperature, what happens is you form oxychloride species on the surface of the metal. So in this interpretation, it's rather a question of chemistry than chlorine mobility in the support. When we increase temperature, you not only move chlorine in the surface, but the metal particle. So the point is normally that when we increase the temperature under oxygen, what happens is that at 250 degrees, you form oxychloride species. That exactly you see by XF. And that way, you still see platinum-platinum coordination, because the oxychloride species are only formed on the outmost surface of your platinum crystalline. So one interpretation is that can be also a question of chemistry. At 250 degrees, it's just enough temperature in order to form your oxidized chloride species. And of course, this will be a function of the number of crystallites and also the number of chlorine on the surface.
Be my guess. However, the morphology of these particles doesn't change that much. Because we can get rid of the chlorine, we do the chemisorption, and we can get back with the chlorine prepared catalyst. We can get back to the same activity as a reduced catalyst that it does not contain chlorine. So they are surface species, no question about it. And of course, they got to agree with the right chemistry. No, I don't want to invent new chemistry here.
One more question.
Yes.
One quick question. Well, what is the chemical driving force to transfer chlorine from aluminum onto platinum? What are the thermodynamics of that? I'm kind of surprised to see that, migration in that direction.
Well, that's a good question. Chlorine exchange with OH on the surface of the alumina to start with. So as chlorine leaves the surface, it's going to find, guess what? Alumina, right? It's going to exchange and it's going to be held very strongly on the alumina. And if you keep reducing or oxidizing the catalyst, this process will take over, and that rate is not very fast in the case of alumina, but it's a lot faster on silica, okay? So on silica you can move chlorine out of the material. Remember, chlorine is going to go to the gas phase, but it's going to collide with the support and back to the surface. It's like a chromatographic effect. And if you do it long enough, sure enough, your peaks are going to be eluted and come out of the catalyst.